Hi folks, welcome to this video on revisiting optimization in differential calculus. We've already had video lessons on doing some optimization before, but we're just taking a look here in a different context for economics and also looking at another one with trig. So the big idea in an optimization question is it's a question where you're looking for a max or a min. Often we've got these 5 big steps here. But you may end up with situations where it's easier than this, where they just give you a function and ask you where the max or min is. We will go over how to do that both analytically and with your GDC. In this question, we've got the cost per item in euros to produce X items is given by this contrived cubic function. We're going to find the number of items that need to be produced in order to minimize the cost. We're going to justify our answer. And we're also given the restriction that X has to be greater than 0, so you're not allowed to produce 0 items. So anytime that you're looking at minimizing something, that means that we're in an optimization situation. So essentially we've got to find out where we're going to find the lowest cost value. And the hack for that is to look at the slope of the cost function. So we can differentiate, and we just get some function that tells us about the slope of the cost function. Now the cost function is probably going to look something like this. There are going to be slopes of 0 at its turning points. And we're wondering where those are. So when we say minimize, we're wondering where is slope, or C prime, 0. If possible, it probably makes sense for us to factor. So we've got this expression here. It may help us just be able to pick out what are the zeros of this function without having to do a whole lot of extra algebra. Okay, so there I have it factored. Where is it equal to 0? Well, I could just put 0 here, but I think it's pretty clear that it's going to be 0 at 1 and 3. Okay, those are the places that the slope of the cost function is 0. So one of those spots we're going to have at least a local minimum. Let's do a little sign diagram on C prime to figure out what's going on. So I can look at x values of 1 and x values of 3. And what I'm wondering is, how does cost change around them? If I put in a number between 0 and 1 into this cost function, and I know it doesn't make sense to make 0.5 of something, but let's just go through the sort of abstract idea here. If I put in 0.5, I'd have positive times a positive times a positive. C prime would be positive, which means cost would be increasing, which isn't great from a manufacturing point of view. If I put in something between 1 and 3 into this C prime, I'm going to get a positive, or 3 times a positive times a negative. So C prime will be negative, cost is decreasing. So what we learned there is that over the first little interval, cost is increasing. You've got a max at x equals 1, which is not what we're looking for. If I put in a C prime or if an x value bigger than 3 into C prime, I'll get a positive times a positive times a positive. It'll start to increase again. So we go from decreasing to increasing. There is a minimum at x equals 3. We can say that we minimize cost by producing 3 items. Another way that you could justify that your minimum occurs at 3 is to use the second derivative. So C double prime of x is going to be 6x minus 12. And if you sub in 3 into this, you're going to get 6 times 3 minus 12, or most importantly, a positive value. So C double prime at x equals 3 is positive, which means we're concave up, which means it looks like this. And so it must be a minimum at x equals 3. So there's the justification, either with the first or the second derivative. Now, if this is a paper 1 question, with the justification, maybe this is worth 4 or 5 marks. If this is a paper 2 question, it's probably only worth 2 or 3 marks, because all we need to do is graph it and find its minimum. So let's go through that process. Here I have the function written in as y1. I'm going to graph it just with standard window settings. And I can see here it's not that helpful. So we do have to do a bit of thinking. In this cubic function, there's a y-intercept of 50. And we don't need to see negative x values. So I'll head to my window settings. Maybe for my x min, I'll make it 0. And maybe for my y max, I'll go all the way up to 100 maybe. And here we can go ahead and we can see what's going on this function. You can see a minimum's occurring. I'm going to press second trace to find it. So I press 3. I tell it a left bound. So from that left bound to the right bound, may be a hair different on your calculator. It tells me that there's a minimum at x equals 3. And at that minimum, y equals 50. So this is an easy way to tell. Now you might also notice that when x equals 0, y equals 50. So if the endpoint could have been included, which the question said that it wasn't, x had to be greater than 0. But if x could be 0, then that would be the location of another minimum. Sometimes you do have to check the endpoints if they are actually included. And in that case, you'd minimize the cost by either producing 3 items or 0 items. Though producing 0 items probably isn't going to bring you a lot of revenue. In this question, we're doing our basic optimization stuff. Anytime you're looking for max or min on a function, differentiate, find where the slope's 0, and then just justify that it is either the max or the min that you're looking for. Let's move on to something that is a little more involved. So we've got a rectangle inscribed under the curve f of x is 4 cos of x over 2. And I'm just going to rewrite that as f of x 4 cos of 1/2 x. They mean the same thing, but if you have to differentiate, it may be easier with the 1/2 x, thinking of it as a coefficient. Points A and B lie on the x-axis. C and D lie on the curve, as shown in the diagram. And they make a rectangle. The coordinates of B, so that's right here, are x, 0. And the coordinates of D are x and f of x, essentially, or 4 cos of x over 2. So it's asking us to do a few things. I think in the end we'll probably end up optimizing or finding the maximum area for this rectangle. But first off, we're supposed to write expressions for the lengths of A, B. So from A to B, this length here is x. This length here is going to be another x. So AB has a length of 2x. And we're supposed to find a length for BD. So BD is right here. And it's just the height. So it would be the y value of the point D. So BD is going to be 4 cos of x over 2. Write an expression for the area in terms of x. Well, the area is just length times width. So that would be 2x times 4 cos of x over 2. Or better yet, 8x cos of x over 2. Or if you prefer, 8x cos of a half x. All these things are reasonable ways to write this. Now we're going to find a prime. So it's probably working us through being able to find an optimal value. A prime might help us to find a max or a min. This is a product rule situation. So if we're using the fact that the derivative of uv is u prime v plus uv prime, then we'd say our u is 8x, our u prime is just going to be 8, our v is all of this, v is cos of a half x, and v prime then is going to be negative sine of a half x times, from the chain rule, a half, or negative 1/2 sine of 1/2 x. And now we just plug and chug. A prime of x, or the rate of change of area, will be u prime v plus u v prime. Not cosine, but sine. Sorry. And we can clean that up a little bit. Now, if we were going to use analytic techniques to go ahead and find the maximum area of the rectangle, we'd want to know where that is equal to 0. So part D says, hence, write an equation to find the x value that maximizes the area of the rectangle. Okay, well, to do that, we'd want to know where a prime is equal to 0. To find our max or min, we just want to know where the derivative is equal to 0. I don't need to go any further with it than that. I've already defined what a prime is. So I could go ahead and solve that equation. I guess I could write it out. But analytically, that's going to be a miserable equation for me to solve. So I'll probably do it graphically. And that lets us know that, we can solve it with the derivative, but in part E it says find the x value that maximizes the area of the rectangle. I think what makes the most sense here is just graph a of x and find its max. So you can take your pick. But if you have techniques that don't rely on getting, say, a derivative correct, then that's probably the thing to do. A of x is also a simpler function, so let's type it in. So there we go. There's the function a of x, 8x cos x over 2. Before I graph, I probably want to make sure that I'm in radian mode. And in the absence of any other insights, I probably want to choose just a standard window setting. So I'm going to press zoom 6. And I can see that max. Okay, there are ones with negative x values. That's not what we're talking about. We're talking about a value that's going to be somewhere between 0 and pi for our x value. So let's go second, calc, and then find a maximum. And I need to go a little bit to the left of that maximum, which is probably hard to see on your screen. And then I go a little bit to the right. And it's going to tell me that there's a max at 1.72. And then it gives me the y value. And here the y value means the area. So it happens to tell me the maximum area as well, which doing it with a prime would not do. So there's a little sketch of the graph that I was looking at. That's enough to communicate what my technique was. And now I know that x equals 1.72 maximizes area. Some optimization questions will also have too many variables in them, and so you'll need to re-express in terms of another variable. And we've done a bunch of those before. But I just wanted to touch on a couple here where you could do it very simply, and one where we had some trig involved. You can find practice questions on page 558, 1, 2, 4, and 5. I think 3 is a little trickier. I hope this has been helpful. Good luck with the material, and take care, folks.